welcome back to Learn as You Explore. If you are new here, I'm a robotics software engineer who loves helping students learn robotics and supporting teachers who teach it. If you're excited to grab the mBot2 or any accessories, check out the links in the description. If you use the links, I may earn a commission at no extra cost to you. Alright guys, let's first take some time to review the ball tracking program from our last tutorial. With this program, the robot would move forward as the ball gets away from it, but it would not move backward while the ball gets close to it. We started off by turning on the fill light for the camera and switching to block color detection mode. We then have a variable to set our max power to 25%. This is the maximum speed that the robot will drive at when the ball is furthest away from the robot but still in the field of view of the camera. We then have a variable that says max y coordinate, and we've set that to 207. Remember that we did a Google search for the Pixie camera solution in the color connected component mode, and we found that 207 is the maximum y pixel value. Then we have our scale factor. Our scale factor is used to convert a y coordinate value into a motor power value. The y coordinate value, when divided by a scale factor, results in a power value that we can use to command the wheel motors. So in short, the scale factor is used to convert a y coordinate value into a wheel motor power value. We then start the loop where the core of our logic resides. First, we get the detected y coordinate of the color block and set it to a variable ball y coordinate. When the ball is within the view of the camera, the y coordinate value is going to be between 0 and 207. When it is outside the view of the camera, the ball y coordinate is going to be 0. We only want the robot to move when the ball is within the field of view of the camera, at which point the y coordinate is going to be greater than 0. That's why we have this if block here, and as long as the ball is within the view of the camera, we compute a wheel power, and this wheel power is going to be the max y coordinate minus the ball's current y coordinate that we got from the smart camera. This difference in the y coordinate values is then divided by the scale factor to convert it to a wheel power percentage. We then print the wheel power and finally command the wheel motors. The left motor's wheel power is directly the computer wheel power, and the right wheel power is inverted by multiplying with -1. This is because when the right wheel is commanded a positive power, it drives backwards, and when it's commanded a negative power, it drives forward. Hence, we need to multiply by -1 to invert this behavior. Finally, when the ball y coordinate is 0, which means that the ball is outside the field of view of the camera, we will stop all the motors. And that is pretty much the logic of this program. If you're a passionate teacher, check out the educator packs I've put together, linked in the description. So why did we spend some time now looking at the previous program, and how does that help us for the current program? Well, for one, we're going to be building on this program to achieve ball tracking both forward and backward, like we saw in the demo in the beginning of this video. Secondly, there are some core concepts here that are somewhat hidden, and I wanted to bring those out and explicitly state them. The hidden concept that I'm talking about is error minimization. To perform error minimization, we need a target value and a measured value. Whenever there is a difference between the target and the measured values, there's a non-zero error, and we can design our system to perform some actions that reduces that error down to 0, or at least close to 0. In this case, our target value is the max y coordinate. The measured value is the ball y coordinate. The error is max y coordinate minus ball y coordinate, essentially this term. And the action that the robot takes to minimize this error is to drive forward with some wheel power, and this wheel power is proportional to this error. So the larger the error, the greater the wheel power, and the smaller the error, the lower the wheel power. This is the core concept that I wanted to bring out and highlight to you, because if you understand this core concept, it is very easy to change this program to make the robot go forwards and backwards rather than just forwards like this program currently does. So how can we do this? Once again, we will rely on the error minimization technique. So this time, instead of tracking the max y coordinate as the target value, What happens if we start tracking the center y coordinate as the target value? To understand the changes that will happen when we change max y coordinate to center y coordinate, let's follow along and see where the max y coordinate variable is used. For one, the scale factor will change because instead of tracking the max y coordinate, we're now going to change this to center y coordinate. But that's fine because that is still going to result in a value that will still make the scale factor convert a coordinate value to a power value when we divide by the scale factor. Next, we use the max y coordinate here in our error term. So if this does get replaced by center y coordinate, now center y coordinate is the target and ball y coordinate can go anywhere, which means this error term can be both positive and negative depending on where the ball coordinate ends up. And previously, this error term could only be positive because we were considering the max y coordinate as the target value. Now, since the wheel power computed is proportional to this error term, you can now see that the computed wheel power could be positive or negative depending on where the ball is within the view of the camera. If the ball is more than halfway above the frame, it means that the ball is going further away from the robot. The error term becomes positive, and hence the wheel power also becomes positive, commanding a forward motion to the robot's wheels. Whereas, if the ball is in the bottom half of the frame, it means that the ball is closer to the robot. The error term becomes negative because at the bottom half of the frame, the value of ball y coordinate is larger than center y coordinate. As a result, the wheel power is also negative, and that makes us command a backward motion to the robot's wheels. Okay, great. Now that you know and understand this concept, let's actually implement the changes that are required. And you're going to be super surprised on how simple it is to make this change. Let's go to File and save this as a new project. I'm going to call it Forward Backward Ball Tracking. Say OK. Like we discussed, let's change the max y coordinate variable to center y coordinate. Go to Variables, find the max y coordinate variable, right-click it, and say Rename this variable. Instead of max, we're going to call it center y coordinate. Say OK. Our variable has now been renamed, but it's not enough just to rename the variable. We also have to set the value to half of the original value. Since this was 207, half of this value would be 103.5. I'm just going to round that to 104. And guess what? That is all the changes that you have to make to get this program running. When button A is pressed, we turn off the light and we clear the screen, but let's also stop the encoder motors here. So right-click, duplicate this block, and insert it here. And that is everything that you need. Select Save, and you're ready to upload the code to the robot. Click on Connect, make sure the COM port is correct, and say Connect again, and click Upload Code. Wait for the code to be uploaded to the robot. Let's go ahead and test it out on our robot now. Here are some of my other videos that you may find helpful. Happy programming, and I'll see you in the next one.